in this one stationary. So this helps us to reduce unnecessary vibrations. Right? And when we want to remove it, we open this tap. Right? So when water goes out, it's slowly removing it. So this looks like very simple, but this very helpful technique. This is the innovation we are proposing, because any other technique there can be vibrations, and this is simple technique, very cost effective, and so on. So this is the regiform table, and we use the weight to control unnecessary vibrations and so on. Right? So you can do it number of times depending on how many layers you require. Right? Then finally you have to apply the aluminium coating. There's a special machine to do that. This is the final view. Is from one side you can see aluminium dots. So aluminium layer for counter electrode. Now ITO is one electrode. The ITO layer next to the glass. The other electrode would be these aluminium dots. So each dot can act as one electrode. Thin film of aluminium was coated by using vacuum evaporation technique as the back contact on the polymer layers. This evaporation was done using Edward vacuum coating instrument. Now if we take optical properties of material being used, this is only when using ITO glass without adding any layers. So this is the characteristic. You can see wavelength and different colors of light, visible range. So comparatively absorption is less visible. Absorption increase at UV region. Anyway, after adding layers, this is after adding one layer, the PMA layer, but we need another layer to see the difference. Right? So you can see at this wavelength, it's 520 nanometers, get the maximum absorption. So that's the range this cell can use to get maximum energy. So we compared with adding many layers. This is with one layer, this is the absorption, the proportion. So with adding many layers, absorption increases. But you can see the initially there's very high increase, and after a while the increase is very low. So we can stop somewhere here also, because no point of adding more layers. These are experiment results, shows how the distribution is. Same thing in a different way. So initially this number of layers, so initial increase of absorption is higher, and after this number of layers the increase is very low. So we can stop somewhere here, because adding more layers causing again the earlier I explained this theory, the when thickness increases absorption. Okay. So during question and answers I may explain if there's any questions.
Yes, I have two questions to Dr. Koggalage. Usually these semiconductor-based solar cells have a long life. What can you say about the polymer-based lifetime of the polymer-based solar cells? And does the lifetime depend on the method of formation? That's my first question. The second question is, how do you bring the terminals into the cell in practically? Because if you want to extract energy, you need terminals, no?
Yeah. First question, the lifetime of the layers. Of course, it depends on the technique you apply. But this Coulomb attraction, it's quite long lasting. In fact, we haven't tried that long because this experimental level. In fact, our focus is not about the chemical formation and so on, but this is being used. This, solar cell production. They are using this kind of layers. So our focus is not about the chemical, the layers, the content of those things, but to improve the method presently they are using. Lot of experiments going on to improve this method because existing solar cells are very expensive. That is why even Sri Lanka we cannot use. Recently it reduced nearly about 50%, but still it's expensive. But this ISAM technique, if properly used, it's going to be very cost effective. Even I think Sri Lanka also we can produce those things. We don't have to depend on other countries. That is one major advantage. So lifetime, of course, depend on the chemical structure and also the technique you apply. But this method we observed that we can add few layers and it won't affect the inner layers. Then I hope I answered the first question. The second one you asked about electrodes. Now two electrodes. One is the ITO layer one side. The other one is the aluminum dots side. So these dots, in fact, you can connect to form one cell. So this is the, inside of a cell. Then of course you need to have other, connections to get outside. In fact, I couldn't show that the next slide. How we test this formed cell. So we apply a light and measure the open circuit and closed circuit voltage and current.
I just want to check whether you are aware of the fact that these monolayers may not be uniform right across the border. And you said it's difficult for you to measure also because there's no electron microscope or whatever, right? So are your measurements based on just one set of samples or is there a cross section? So to check the uniformity of the layer thickness?
No, madam, we have plenty of samples, of course. Initially we also expected that like when we immerse and take it out, probably the last portion maybe the thickness will be higher. But practically we observed that is also same as the top. So it's a very thin, equally spread layer, the thickness wise.
But, and, but you haven't measured the thickness, no? So is it just a guess that you, because you take it, immerse it, take it out.
Yeah.
So when you take it out,
so this,
because these are nanometers, right?
Nanometers in the range of.
Yes. So
but that light absorption method, we can get an indication that this uniformity is there. Yeah. So that's what we observed experimentally.